In this lecture, let us talk about noise in double sideband suppressed carrier amplitude modulation system. In the previous lecture, we talked about the baseband communication system. Okay, so what is the figure of merit of baseband communication system? Okay, so we will find the method of analysis for DSB-SC system is more or less the same as baseband communication system. Okay, so we draw the picture of the system now. Okay, so look at the signal input power, signal power input to the receiver, and noise power spectral density input to the receiver, and then signal power at the output of the receiver, and noise power spectral density at the output of the receiver, and so on so forth. So these are the four parameters that we need to consider. I have the receiver, the input is noise plus signal. So I need to consider what is the signal power input to this receiver, and I need to consider the power spectral density of noise. So from this I can find out input noise power. Fine. Similarly, in the output I need to find out the signal power at the output of the receiver, S naught, and noise power spectral density of the output of the receiver, N naught. So these are the four parameters that we need to consider. Now let us draw the diagram for DSB-SC system. If you recall, at the transmitter what you do, you take M of t. M of t is multiplied by cos omega ct. So I have a multiplier. For that multiplier I will give cos of omega ct. So this is my transmitter. This block is my transmitter. So let me introduce a constant here, this root 2. Even if you don't introduce, nothing will change, but I am introducing this root 2 to simplify the analysis, that's it. Okay, this root 2 has been included to normalize the message power to the same value as before what we had in a baseband communication system. Okay, that's all, multiplying the message signal with the carrier. And this root 2, either you like it, you can add it, or don't do it. If you multiply by root 2 cos omega ct, then the manipulation and algebraic simplification will be very easy. That is the reason I am putting this root 2. Now channel is again we will assume to be ideal. Okay, but it is not going to be ideal low pass filter. The baseband communication system, we said the channel was ideal low pass filter. Now it will be ideal band pass filter. Okay, so that is the only difference. And then the noise is getting added, N of t, right? When I say ideal band pass filter, the frequency components are located at minus Fc and plus Fc. So here this point will be minus Fc minus Bc minus Fc plus B, and here this will be Fc plus B and Fc minus B. This is for high pass filter. If you draw the low pass filter, then it will be like this. Excuse me, minus B2 plus B, and this is my low pass filter. That's it. So now the channel is modeled as an ideal band pass filter. So there will be a perfect flat response. Look at here. Ideal means perfect flat response. Excuse me. Okay, so perfect flat transfer function between Fc minus B to Fc plus B. Now what is the bandwidth now? The bandwidth is 2B and centered around Fc. Okay, so Therefore, it is Fc minus B to Fc plus B. Similarly, we will have in the negative side also, if you look at 2B, between minus Fc plus B and minus Fc minus B. Okay, but the bandwidth is 2B. So here the mathematical bandwidth is 4B for the purpose of calculating the noise power, but conventional bandwidth is 2B only. Mathematical bandwidth is equal to 4B, but the conventional bandwidth is 2B only. So what is the noise power? Noise power, see this is multiplied by the power spectral density of the noise. So the height will be n0 by 2, let's say n by 2. So n by 2 times your 4B, therefore this is 2 times of nB. So this is my noise power. Okay, so please remember, the only effect in the channel that we will consider now is the addition of noise. So that is why I put a addition symbol here. Okay, so we assumed that the channel is ideal band pass filter. Now let us talk about the receiver. Okay, the receiver will have a band pass filter centered around Fc. Why do we need again band pass filter? See, there are two kinds of things we need to understand here. The channel is also modeled as ideal band pass filter, and in the receiver also we have a band pass filter. What is the reason? Because if you take FM transmission, the frequency range will be 88 to 108 megahertz, right? That's what we said. Now if you tune any one frequency, let's say 91.2 megahertz. Now 91.2 megahertz, the bandwidth is 200 kilohertz. That means you will pass from 91 megahertz to 91.3 megahertz. So the center frequency is 91.2, and this side it is 91. So let's say 91.1, 91.1, and this one is 91.3. Therefore, the total bandwidth is 200 kilohertz. So you should have a band pass filter from 91.1 megahertz to 91.3 megahertz at the receiver. Otherwise, what will happen? The receiver will pick up the neighboring channel also. Therefore, in the receiver, my first block will be a band pass filter. Band pass filter which is centered around Fc, and the bandwidth is Fc plus or minus B. And after that you give it to demodulator. So that the demodulator also you will give the same root 2 times cos of omega ct, and then give it to low pass filter. This is my output. Okay, so let me what is this? This is my demodulator, and this whole thing I can say front end of the receiver, or I can say channel. Okay, so front end of the receiver. Channel. So because channel also modeled as the ideal band pass filter. So the demodulator is essentially once again multiplies root cos omega ct, and then followed by a baseband low pass filter. Okay, low pass filter is after all a baseband filter, right? So with the bandwidth of B hertz, let's say the bandwidth is B hertz. Okay, now okay, let me call this point A, and this point okay, let me call this point A, and this is my output B, like that. Now let us try to find out what is the signal power and noise power at point A. Why do we need to find out? Because this is my demodulator. In the demodulator, I need to know what is the signal power and what is the noise power, input signal power and input noise power to the demodulator. Okay, if you calculate here, what will happen? The noise power will be infinity, right? And then you cannot find out a signal to noise ratio here. It is meaningless. Okay, maybe I will make some free space here so that now look at here. In case if you find out the noise power, what is the noise power here? Noise power is equal to integral of power spectral density function, that is denoted by S suffix n of f and df. So that will be equal to integral of n by 2 times df. What is the frequency range? The SNF integrates from minus infinity to plus infinity. The noise is a wide band noise. Okay, it gives equal contribution of n by 2 from minus infinity to plus infinity. Therefore, the noise power is infinity here. So, but the signal power is finite. It is finite. So, finite value by infinite, this is equal to 0. Therefore, signal to noise ratio at the input of the band pass filter, or at this point, let us say this point is C. At C, the input signal to noise ratio is 0. So, it is meaningless to calculate at this point, in this point. But generally, we need to find out the performance of my receiver in terms of its figure of merit. What is the output signal to noise ratio and what is the input signal to noise ratio. Okay. So, let us try to calculate the input signal power to the demodulator, which consists of multiplier followed by a low pass filter and a noise power. And after band pass filter, it is very easy to calculate the noise power. Just now we calculated. So, you have the band pass filter response like this. This is 2B and here also 2B, and the center frequency is FC and minus FC, and here this is FC. So, 2B times n by 2, 2B times n by 2. So, total it is 2NB. Therefore, your input noise power is equal to 2NB. It is simple to calculate before the demodulator. Okay. So, at this point, at point A, let us try to write down the signals. So, let me denote this input signal yi of t is equal to si of t plus ni of t. This si of t is coming through the band pass filter. Okay. So, this band pass filter. So, what is your si of t? Si of t is, if you look at the figure, okay. So, this is my root 2 times m of t. So, this is going to be root 2 times m of t cos omega ct. Okay, maybe I will see. You have m of t multiply by root 2 cos omega ct. Therefore, in this point you will have root 2 times m of t times cos omega ct, and this you will give it to band pass filter, and in between noise is getting added n of t, and in this point we would like to find out what is yi of t. So, your yi of t is root 2 times m of t cos omega ct plus, let us say, input signal power ni of t. Okay. So, what are you transmitting? You are transmitting root 2 times m of t times cos omega ct. So, after band pass filtering, the signal power will be, what will be the signal power? Signal power will be the same. Okay. Signal power will not be changed. Okay. But after band pass filter, the signal will be the Okay, after the band pass filter the signal will be the same. But what about the noise? Okay, here the noise is a wideband noise. It is a wideband noise. What does it mean? The signal exists from minus infinity to plus infinity with the amplitude of n0 by 2. But the moment you pass it through the band pass filter, then in this place it becomes a narrow band Gaussian noise. Okay, so let me write down in different color. This n of t is this n of t is white Gaussian noise. But the moment you pass this white Gaussian noise through the band pass filter, then it becomes narrow band Gaussian noise. Narrow band Gaussian noise. Therefore, the power spectral density of noise will get modified to have a bandwidth of 2B. See here, what is the bandwidth before the band pass filter? The bandwidth is infinity. But after band pass filter, what is the bandwidth of your noise? It is 2B. The positive frequency side 2B, the negative frequency side it is 2B. Okay. Therefore, how do we denote this noise? It is denoted by Ni of t. After band pass filtering, the noise becomes a narrow band Gaussian noise. Therefore, N of t is the white Gaussian noise or wideband Gaussian noise. Here white means it gives constant value for all the frequency. Like when I say white light, that light contains all colors, right? Rainbow. Like similarly, here when I say white Gaussian noise, it contains all the frequencies with a constant magnitude, equal contribution for all the frequencies. The moment you pass it through the band pass filter, output of the band pass filter is denoted by Ni of t. Here this I indicates input to the receiver, input to the demodulator. Okay, so this is going to be narrow band Gaussian noise. That is white Gaussian noise, and this is narrow band Gaussian noise. And now recall this narrow band Gaussian noise is denoted by the quadrature representation. Okay, recall this representation from the previous lectures. Probably before the amplitude modulation, I discussed this. So Ni of t is equal to Nc of t cos of omega ct plus Ns of t sin of omega ct. So this is my Ni. So what is your y? Yi of t equal to root 2 times m of t cos omega ct plus Ni of t. Now substitute this guy in this place. Okay, let me say this is equation number 1 and equation number 2. Substitute equation 2 in equation 1. So your yi of t is equal to root 2 times m of t, then cos of omega ct. By the way, the noise component also located at the carrier frequency. Nc of t cos omega ct plus Ns of t sin omega ct. So we can write the narrow band Gaussian noise in terms of in phase component. What is the in phase component? This guy is the in phase component and quadrature component. Okay, so I have both in phase component and quadrature component in the narrow band noise. Now And what about the symbol of this one? It can be either positive or negative, doesn't matter. Okay, it doesn't make any big difference as far as the properties of the resulting process is concerned. Now from this expression, what is the signal power here? The signal power that you will have here is this power. This is my signal power. Okay, at the input to the demodulator, this is your signal power. This is your signal component. So the power in this component is your signal power of the input to the demodulator. Therefore, my signal component is equal to root 2 times m of t cos omega ct. Let me call this as 4. And then therefore, what is the signal power? Signal power, let me say Si is equal to expected value of root, because it is a random signal, right, root 2 times m of t times cos omega ct whole square. Okay, expected value of this one. Now it becomes expected value of 2 times m square of t cos square omega ct. So this is 2 times m square of t plus multiplied by 1 plus cos of 2 omega ct by 2. Expand this, plus 2 times m square of t cos 2 omega ct whole divided by 2. This 2 and that 2 will get cancelled. So, you will get expected value of m square of t plus expected value of m square of t cos 2 omega ct. Now, what do you think the first will be? This guy. This guy is equal to how much? M square n bar, expected value of square of m of t. What about the second guy? This guy is going to be how much? If you do the integration, the same argument we did while we discussed amplitude modulation, like if you have m square of t times cos 2 omega ct. So this m square of t is a low pass signal, right? Slowly varying signal, and this cos 2 omega ct is a carrier signal with a high frequency. So that means what? So you have like this very high frequencies, and you integrate half cycle by half cycle. Okay, so half cycle by half cycle. So in this portion, we said this height is constant. Okay, therefore this area, whatever the area you have in the positive half cycle, that will be the same as the negative area. Similarly, whatever you have in the positive half cycle, that will be, of course I did not draw the diagram clearly, I mean properly. Let's say my diagram is very bad. Okay, the frequency is constant in AM system, because we are talking about AM system, right? So whatever the area in the positive half cycle, that area will be the same as the negative area cycle. Therefore the total integration will be 0. Hence this guy leads to 0. Okay, therefore my signal power Si is equal to m square bar. That's it. Okay, so this is your message power, and now you see why the factor 2 is included. Now the 2 has gone now, because of that reason only we multiplied by root 2. So this will make sure that Si is going to be equal to m square bar, the same value that you had earlier in your baseband communication system. Now what can you say about the noise power? That we already calculated. Ni is equal to 2b, the negative side, 2b times n by 2. In the positive side, again the bandwidth is 2b times n by 2. So this is 2 times nb. this is my noise power. See, this is your ideal band pass filter, right? That's what I said. The bandwidth is 2B and the height is n by 2. The negative side also minus Fc, and here the bandwidth is 2B and this point is plus Fc. So that's how this 2NB has come. Okay, so this Ni is the input noise power. So this is as far as the input to the modulator is concerned. Now what will be the output of the demodulator? So you are giving Yi to the Yi of the demodulator. The demodulator contains again a product multiplier root 2 times cos of omega Ct and followed by low pass filter. So in this point we calculated Si and Ni, then we would like to calculate S0 and N0. What is S0 and what is N0? Output of your demodulator. It's again fairly simple calculation. Okay, you can do that. How will you do? Your Y0 of t is equal to, how do you calculate Y0 of t? Y0 of t is equal to Yi of t multiplied by root 2 cos omega Ct, and Yi of t already I wrote here. Where is it? This one. Yi of t is equal to root 2 times m of t cos omega Ct plus nc of t cos omega Ct plus ns of t sin omega Ct. So we multiply term by term with the root 2 cos omega Ct. So this I can say root 2 m of t cos omega Ct plus nc of t cos omega Ct plus ns of t sin omega Ct. This is my Yi of t multiplied by root 2 cos omega Ct. So then what will happen? The first term will be root 2 times root 2 becomes 2 times m of t cos square omega Ct plus root 2 nc of t cos square omega Ct plus root 2 ns of t sin omega Ct and cos omega Ct. Now you look at the last term. What is this? Both are orthogonal to each other, therefore this will lead to 0. Okay. Now in this guy 2 times m of t, then cos square omega Ct, you can write 1 plus cos 2 omega Ct by 2 plus root 2 nc of t. Again this cos square omega Ct you can write as cos 1 plus cos 2 omega Ct by 2. Now multiply inside 2 times m of t by 2 plus 2 times m of t cos 2 omega Ct by 2 plus root 2 by 2 nc of t plus root 2 by 2 nc of t cos of 2 omega Ct. This is my output. Sorry, not output, output of the product modulator. I am sorry, I am very sorry, this is not output. At this point, let us say that one is Y1 of t, because there is a low pass filter, right? So I did not consider that. Low pass filter will not allow the high frequency component. So therefore, let me draw the diagram properly. Low pass filter this is the demodulator, and this is, let's say, your y naught of t, and in this point let me call y1 of t. So therefore this point, this is y1 of t. So what is my y1 of t? Y suffix 1 of t. So this is my y suffix 1 of t. Now what is the frequency component in this? 2 omega c. What is the frequency component of this? 2 omega c, very high frequency. So these two guys will not be allowed by the low pass filter. It will reject. It will pass through this one and this one. Therefore output of my demodulator is y naught of t, that is output of the low pass filter, is equal to m of t plus root 2 by 2 becomes 1 by root 2 nc of t. Okay, so this is the output of demodulator. Okay, after low pass filter, this cos 2 omega ct will get eliminated. Okay, this cos 2 omega ct term will get eliminated. Then here also you have cos 2 omega ct term. This term will get eliminated. Therefore the output will be m of t plus 1 over root 2 times nc of t. Now what is your output signal here? Signal part. So this is my signal, right? Therefore m of t. Okay, what is output signal power? S naught is equal to, it is m square power. Same as the input signal power. Now what is your output noise power? Output noise power, you can calculate from this. This is my noise component. Right. So from the noise component you can calculate the noise power. So output noise is equal to 1 over root 2 nc of t. Right. Now noise power, output noise power is equal to square of that. 1 by root 2 becomes 1 by 2, then nc square bar of t. So the important property of narrowband noise is as follows. I already told you in the beginning of this course itself. I don't know how many of you remember that. The band pass noise is denoted by ni of t is equal to nc of t cos omega ct plus ns of t sin of omega ct. Okay, so now what I am trying to say here is the power of nc of t is the same as power of ns of t. Okay, so nc of t power is the same as ns square of t. You can prove this mathematically. Okay, so therefore this is a band pass noise, right? So the band pass noise is again located at a minus fc and plus fc with the bandwidth of, because you have a band pass filter with a bandwidth of 2b minus this one is 2b, and here also this one is, I'm sorry, so this bandwidth is 2b. Therefore in this the noise power is nb, this is n by 2 and this is n by 2, here the noise power is nb, so the total noise power is 2 nb. Therefore the power of in phase component is the same as power of quadrature component is equal to 2 nb. Therefore my output noise n naught is equal to 2 nb. So what is output SNR now? Output SNR is equal to output signal power divided by output noise power. What is output signal power? It is the same as input signal power SI. If you recall what is SI, we just now we calculated a few minutes ago. See, SI is equal to m square bar. So S naught also m square bar. Therefore, SI equal to S naught. Therefore, divided by what is N naught? N naught is 2NB. I'm sorry, 1 by 2, there is one factor. Yeah, this factor I forgot. Okay, I'm very sorry. So, that is okay. But here I did a mistake. I did not include this 1 by root 2. 1 by 2. 1 by 2 times 2NB. Then 2 will get cancelled. So, it becomes NB. Okay. Therefore, SI by NB. What is this SI NB? Recall from your baseband communication system. What is this? This is equal to your gamma. So, therefore, my DSB-SC system provides output signal to noise ratio which is the same as our baseband communication system. So, the conclusion is, as far as signal to noise ratio figure is concerned, there is no difference between baseband system and DSB-SC modulation system. As far as output to signal to noise ratio is concerned, there is no difference between baseband communication system and the modulation system. Okay, so this was something that we could have expected intuitively. So therefore, it is not very surprising result. Okay, so that's it about DSB-SC AM system. Okay, so let me stop at this point. The next class we will continue from this point. Probably we will start with a single sideband modulation, and then we will go to AM system with carrier. Thank you very much.